Hi everyone, today let's look at some of the most common memory leaks that happen in C or C++. To start off, we have this no deallocation where you have allocated some memory in the heap and you are not freeing it explicitly. So in line number 12 and 13 you can see that I'm allocating 10 bytes of memory, one using new and one using malloc, so I have to free them using delete and free. Let's see what happens when I don't do that. So as you can see, the program executes successfully without any issue, so this memory leak goes unnoticed. Now Xcode provides us a cool memory profiler that can help us identify this. So go to this product tab, click on profile. So these are the various kind of profilers that Xcode offers. Click on the leaks one. Okay, now let me just run this. Okay, and I have hit this breakpoint. I go back to the profiler, and actually I can attach it to any process. So here I'm attaching it to my program that's running Xcode debugging 101, and I'm starting this profiler. Let's run this program and see what happened in the profiler. Yeah, it's showing me a leak has happened here, and these are the two address locations where leak has happened. So this is corresponding to this two allocation that I have not freed. Now let's delete or free this and try again. So stop it and stop this profiler, run the task again, and again attach the profiler. Yes, let's see what the profiler has picked up. Yeah, now no leaks happens. As we can see that it's following this red check, the green checkbox, which means no leaks have happened. Yeah, moving on. Some other scenarios where leaks can happen commonly is one is the wrong deallocation, where you have allocated some memory but you are using the wrong delete operator here. What you should have used instead is this delete operator with parenthesis. Actually the compiler shows us this warning message that we are using the wrong delete operator, so that will be helpful to catch this issue very early on. So let's correct it. Yeah, moving on, the next common case is the pointer reallocation, where you have some pointer which has been allotted some memory, and you are allocating a new memory chunk to this pointer without actually deallocating the first one. So to solve this, we have to delete this memory before we allocate any new memory to this buffer. Something that's similar is pointer reassignment. So if you have a pointer that is pointing to some memory location and there are no other pointers pointing to that location, then if you assign this pointer to a new address or assign it to null ptr, there is no way to free this memory now. So that's why you have to always make sure that if you are assigning some new pointer to already existing pointer holding a memory, you have to delete it. And this is very common in production level C++ code, because often a function may be returning a pointer, and for a programmer who is not aware of who should take the ownership of deallocating a memory, these kind of errors are very common. Okay, that almost covers most of the scenarios of memory leaks in C and C++. Now let's look at the memory leaks that happened in object-oriented programming specific to C++. So a bit of primer here. Here I have a derived class that is derived from a base class, and I have overloaded the constructor and destructor of these classes to print out they have been invoked. Now let's try something out. Now what I have here is a pointer to a base class which is pointing to an instance of a derived class. Let's see what happens when I call this delete operator. So yeah, run it. So we can see that the constructor of the base class has been invoked, then the derived class has been invoked, but the destructor of only base class has been done. So the memory leak has happened for the instance of derived class. So this happened because we have not made this destructor of the base class virtual. So once we make this destructor of the base class virtual, it has a vtable pointer that points to the destructor of its derived classes. And so now when we run the program again, we can see that the derived class destructor is being called before the base class gets destroyed. Now let's move into a bit more involved example. Let's say we have a container class that have some pointer to pointer that is pointing to some memory location. So here I have a derived class pointer. Now yeah, so in the constructor I'm just assigning a new memory location to this pointer, and in the destructor I am deleting that. So let's see how memory leak can happen here. So here I'm instantiating a C1 class and then trying to copy that C1 class into C2 using this default copy constructor. So C++ by default implicitly creates this copy constructor. It's also equivalent to this, which does a shallow copy, and let's see what happens in this case. Yeah, so what happened here is we have okay, so we have a PTR for the class C1 and that's here, and so we have a PTR for C1, and the PTR for C2 would be pointing to same location as PTR of C1. This is because we did a shallow copy, not a deep copy. So what's going to happen is once this destructor of C1 is called, this memory is going to be freed, and now when when the destructor of C2 gets called, the same we are trying to double free a memory that's already been freed. So that is going to give us this error and this memory leak. So how can we get rid of that? Well, we need to override this copy constructor here, and here what I'm basically doing is deleting this pointer, and I am allocating a new deep copy for this PTR using this copy constructor of this derived class. So let's try running this again now. As you can see, we have 4 constructor calls and 4 destructor calls, so there is no memory leak happening here. Now let's also look into some more examples. So although it looks like we are doing some kind of an assignment here, this actually invokes the copy constructor. If I run this, you can see, so it works properly. It's the same as the first the case I discussed before. But if we were to do some kind of an assignment operator, since we have not overloaded it, it uses the default compiler generated assignment, which does shallow copy, and we run into the same issue. And so if we modify it like before and do deep copy instead and try to run this, let's see what happens. So yeah, we can see that there are 1 2 3 4 and 5 6 constructor calls. 1 2 3 4 5 6 destructor calls. So there is no leak that's happening now, but there is a problem. If we were to do something like this, and this is called self assignment, which is a valid operation where you are assigning c1 to itself. In our overloaded assignment operator, we have not handled this case. So what this will try to do is c and this pointer is now effectively the same, and when I delete the pointer and try to copy this pointer inside c, it has already been become a dangling pointer because I have deleted ptr here, and that will also be reflected on c.ptr. So for that we need to do this self assignment check, in which case we check the address of c as well as this, and if that's a self assignment then we don't have to do anything here. Okay, let's try doing this. Yeah, we have entered the self assignment, hence we just return from here. So that's pretty much covers most of the memory leaks that are bound to happen in C++. Now let's look at how we can prevent them. So here I have jotted down some of the common ways that you can prevent these kind of memory leaks from happening. So use delete and free as sparingly as possible by making use of smart pointers. I'm going to discuss them in detail in a follow-up video. Also, if you are forced to use this dynamic memory allocation, then always pair your new and delete, and yeah, you guys can go through the rest of the pointers that I have jotted down here to make sure such kind of nasty memory leaks doesn't occur in your code. Thank you.